just sitting here and you guys are staring at me, so I'll go ahead and get started. It's close enough to noon. What we wanted to talk about today is proofs. I don't know if you guys remember, it's been 2 weeks since we've met, but before that very long spring break, we had a test that was all about proving stuff. And so we had different proving techniques. We could prove things using direct proof. We could prove things using contrapositive. We could prove things using contradiction. Or we could show existence or uniqueness. Today what we're going to focus on is disproof, or that is proving something is false. Now, in order to prove something is false, really all we're going to be doing is recalling that not P is true whenever P is false, and not P is false whenever P is true. Therefore, if we want to show that a statement is false, what we really do is we find the negation of the statement, and we show that the negation is true. So, you negate the statement, and then show it's true. Now, once we negate the statement, which we've done before in class, we've spent a lot of time on that. And when we're doing the logic, I wanted to spend time on that because, again, this is coming up to be important. And then we also spent time on all of our proofs. So obviously we'll have to go back and do some more practice with that since it's been a while. But we'll convert these into things we can prove. Now, once we get into that though, the only new step is that now we're actually going to be stuck with theorems where we don't know if they're true or false. That is, you'll be given a statement and you'll have to determine if it's true or false, and then you'll have to give a proof of your decision. So a lot of times this is what you end up seeing is there's a some statement and you have to determine is that true or false. And so let's just start off with our theorem here, which may or may not be true, is let's suppose that x and y are real numbers. Is it true that the absolute value of x plus y is equal to the absolute value of x plus the absolute value of y? Well, let's go ahead and look at that and think about that for a minute and say absolute value of x plus y, absolute value of x plus y. All right, so I'm going to come over to the board. I think I'm writing this in the other order, but we want to determine is that true or not. So how are we going to do that? Well, the first thing we need to do is just check it for some numbers. If I say plug in 1, 1 plus 2, so x is 1, y is 2, is that equal to 1 plus 2? And I end up with absolute value of 1 plus the absolute value of 2 is 3. 1 plus 2 is 3, so absolute value is 3. So yes, 3 is equal to 3, so this seems to work in this case. Since I should try real numbers, I should try other things too, like 1/2 plus pi. Is that equal to 1/2 plus pi? So here I have some rational and some irrational, but I'm adding 1/2. Absolute value is 1/2. Absolute value of pi is pi. So I get 1/2 plus pi. Over here I get 1/2 plus pi. So what we end up with is so far so good, but is that going to work in general? Maybe I should try other numbers. What other numbers should I try? Anybody have any suggestions? Very good. So we have a suggestion of some negatives and some positives. So let's pick, I don't know, -1 and 2, and -1 and 2. And then I get, well, the absolute value of -1 is 1 plus 2. But over here I get -1 plus 2 is 1. And so I get 3 should be equal to 1 if this theorem is true. But notice 3 is not equal to 1. Therefore, we have that this theorem is going to be false. So, if we want to prove that the theorem is false, That is, our original theorem was for all x and y real numbers. We have that the absolute value of x and y are equal to the absolute value of x plus y. So what we want to do is we want to negate that statement. So to negate a for all, we get a there exists. So I'm going to first write down the negation. So there exists an x and y in the set of real numbers such that, and then I have to negate the statement. So that would be absolute value of x plus the absolute value of y is not equal to the absolute value of x plus y. So what I've done now is I've taken my theorem, I've negated it, and so now I'm going to prove this. And remember now, oh, I forgot there exists. But now we have an existence proof. So this goes back to the proofs that we were talking about before. And so for an existence proof, we just have to find an example. So what we would just say here is, note, we've already had the example, so let x equal -1 and y equal 2. Then we do have that x and y are real numbers. Also, we get that -1 in absolute value plus 2 in absolute value is equal to 1 plus 2 is 3, but -1 plus 2 is equal to the absolute value of 1 is 1, and 1 is not equal to 3. So we've proved the negation of the statement. Hence, we have proved that the original statement was false. Any questions in there? So I am trying to follow your guys' chat as well, but when I'm at the board, it's a little bit more difficult. That's why I was setting up this Discord so you could talk. Somebody has talked, one person, but otherwise nobody is talking. That's why Discord is quiet. All right, so the chalkboard looks rough. I'd have to be bigger about this, so I'll rewrite some of that. All right. I think the big thing is I just need to be bigger, and I'm still getting used to this, so I apologize. But I'm going to say there exists an x and y and r with the absolute value of x plus the absolute value of y not equal to the absolute value of x plus y. And remember, our proof was let x equal -1, y equals 2. Can you not hear me anymore? Hello? All right, does the board look better there? By the way, I hear someone talking in Discord. During the setup, I had it set up so that I'm not talking in Discord, so that you don't get the repetition of my voice. All right, thank you guys. All right, so then I'll move on. And my next theorem is going to be let A, B, and C be sets with A cross B equal to B cross C. What I want to know is A equal to B? So is that going to be a true theorem or is that going to be a false theorem? And so what we need to do is some work and test things out. I'm actually going to give you guys a minute and try a couple of sets A and B and C and see if you can come up and determine if this is true or false. While you do that, I'm going to write some stuff on the board so that it's nice and big and we can see it. All right, have you guys come up with any suggestions for A, B, and C? Do you think this is true or false? So we're going to take A cross B, so the Cartesian product of two sets A and C. And then we're going to try to show that that's equal to the Cartesian product B and C. Then we have to have the case that A is equal to B. So I just want to know, is that true or false? All right. So what I have here is I'm just going to set A, B, and C. Let's say A is A, B is B, C is C. So I'm just going to try to make really easy examples here. And then if I do this, what I end up with is, what is A cross B? Or A cross C, rather, is going to be the set consisting of the element AC. And B cross C is a set consisting of BC. Now the idea here is that what we want to assume is that A cross C is equal to B cross C. And so I'm just going to think, well, what would have to happen in order for these two to be equal? Well, in order for these two to be equal, I'd have to have AC is equal to BC, therefore A is equal to B. So therefore, in order for A cross C to be equal to B cross C, we must have that A is equal to B. So in this case, this would have to be an A as well, and I would get that. So what we're seeing here is that if I have something like this where it's one element each, and I'm going to take A cross C and get B cross C, then it would have to be the case that A is equal to B. But in general, is there any other thing I could try here? Is, well, I could try, well, if there was an A and B here and a C here, then I'd have A, C, B, C. I'd have to have A, C, B, C over there for this to be true, so A would have to be equal to B. If I add in more elements here, what it's really looking like is that if this is equal to this, then this would have to be equal to this. And so it's looking like this is going to be true. So how would we prove that? Well, what we'd have to do is we'd have to assume this and then show this, or we could do a contrapositive and assume the negation of the then part and show the negation of the if part. And so we could walk through and we could try to do this proof. The one thing I want to point out here is that this is looking like it's true for most sets, but what we do end up with is if we actually think very carefully and we let C be the empty set, then we do get something happening here that's not going to quite work out. And so if I take, let's just say A is A, B is B, then A cross the empty set is the empty set, and B cross the empty set is the empty set. Because if we try to take ordered pairs with things in the empty set, we have no options. So actually we get A cross the empty set is B cross the empty set. Now we wanted to show that for any C, if A cross C was equal to B cross C, A is equal to B. But what we notice here is that that's not necessarily the case if C is the empty set. So even though this one seemed to work out to be true in general, it works out most of the time, but it doesn't work out if C is the empty set. And so the point I'm trying to make here is that if I think about if AC is equal to BC, does that imply A is equal to B for real numbers? Well, most of the time I can divide by C and get A is equal to B. The only time I can't is if C is 0. So we're using a similar example here to say C is, instead of being 0, it's the empty set. So if I take the direct product of these two, I'm going to get the same thing, even if I didn't start with the same thing. All right. So just to bring back the theorem real quick, we said let A, B, and C be sets. Then if AC is equal to BC, we have to have that A is equal to B. What we're going to do then is give an example. So our proof would look like let A equal the set A, B equal the set B. If you'd like to, you could use 1 and 2 here, and C equal the empty set. Then A is not equal to B, but A cross C is equal to B cross C. And so we're showing the negation that there exists a C such that there exists an A, B, and C such that A cross C is equal to B cross C, but A is not equal to B. All right. Do you guys have questions on that one at all? All right. If you guys do have questions, just type them out or ask me. If I miss your text, it's just because I don't have the text in front of me while I'm at the board, but I will get to it as soon as I see it. Let's try another example. Here we have A, B, C, and D are sets. Then A cross B union C cross D is equal to A union C cross B union D. All right, so do we think this one is going to be correct? How about, just to make sure you guys are listening, just take a wild guess if you have to and say true or false. So T for true, F for false. Do you think this theorem is true or false? All right, I got one vote in. Thank you, Kate. I appreciate it. I was trying to do this. I forgot to switch. Sorry about that, everybody. All right. Going back to this, though. I have a couple falses. All right, good. So, if we think this is false, we have to come up with an example. And so we have to think about what would A, B, C, and D look like in order for this to be true or false. And so, Dylan, you can vote in there or on Discord. Either way. Um, I'm not keeping up with the Discord chat, but if you talk in Discord, I will hear you. I just have too many screens to try to pay attention to. All right, back to the point here is we're trying to determine if this is true or false. And so we want to think about, can we just try some different examples? And so I would try something like A is A, B is B, C is C, and D is D. If I take A cross B, it's going to be the ordered pair AB. Um, so to answer your question, Lil, you can type in YouTube, talk in Discord. That would be my preference. If you type in Discord, I will see it. It will take a little bit longer because I'm bouncing back between all the screens. All right. So, anyway, going back to this one, I'm going to go up at the board and just write down what happens if I let them be that example. And I'm going to get A cross B is just the single ordered pair AB. And C cross D is a single ordered pair CD, because I'm just letting my sets be the single elements A, B, C, D. And so if I take, on the one hand, um, just need to remind myself, A cross B union C cross D. So the union of these two is going to be the set consisting of AB union CD. I know this is probably messy in here, so. So the union of these two is AB union CD, or I should say as a set, just those two elements. All right, so I have two elements. Now on the other hand, if I take A union C cross B union D, I get A union C is the set consisting of AC, and then I'm going to take the Cartesian product with the set consisting of B and D. And notice already, without even finding what these things are going to be, because I have two elements here and two elements here, I'm going to end up with four distinct elements. In particular, A, B, A, D, C, B, C, D. So what we have is, if there's four elements here and only two elements here, these can't be the same sets. So what we've found is, just by going through and picking a simple example where each thing consists of one element, where A and C are distinct, or B and D are distinct, we end up with a counterexample to our proof. So what that means is we have an example to the negation of our theorem. So therefore, that would be, giving this example and writing that up, would be the proof that this theorem is indeed false. So a lot of times what we're going to end up doing is just really going through, trying examples, and seeing what happens. Sometimes examples show the theorem's true or the theorem's false, and it isn't enough. We have to do more work, but sometimes just getting one example is enough to disprove a theorem, which is what we had here. So we keep going until we're relatively convinced of whether it's true or false, and then we move on. All right. We've had a lot of false theorems. That was probably bad planning on my part. I probably should have thrown a true one in there just to liven things up. Well, here's a true one. For every p and q in the rationals, if p is less than q, there exists an r in r not q, such that p is less than r is less than q. So what we're saying here is that between any two rational numbers, I can always find an irrational number. So I'm telling you that's true because I actually want to prove it. So how would I prove something like that? Well, the idea is that I have to pick any two arbitrary rationals, I can't say like 0 and 1 and find an irrational between them. I have to say something like P and Q are just rational numbers. I then have to find an R which is strictly larger than P and strictly less than Q. All right, so how are we going to do that? Any ideas? So let's suppose I have P and Q and Q. Now, if P is equal to Q, this isn't possible, but we're going to assume that P and Q are not equal. So, because if P is equal to Q, clearly we can't put anything between there besides P and Q. But if P is not equal to Q, then what I get is either P is less than Q or Q is less than P. So I'm going to assume that P is less than Q, because if it's the other way around, I'll just relabel, and then I'll have P is less than Q. Now, what I want to start off is instead of trying to just put a irrational number between these two, because that's going to be a little bit more work, can I find a number which is between any two numbers? So if I pick 0 and 1, I want to put something strictly between them. Hopefully you guys can help me out here. What's the number between 0 and 1? Very good, Dylan. That is exactly what I was going for, is the average of the two. So, so if I take 1/2, very good. 1 plus 0 divided by 2 is 1/2. 1/2 has to be between them. And so if I take this and I say P is less than, and if I take the average, P plus Q over 2 is less than Q, we know that P is less than P plus Q over 2 because P is less than Q. So therefore, this is less than 2P over 2. So this is strictly less than the average. And this is strictly less than Q because if we take 2Q over 2, we know that P is less than Q, so it's less than 2Q over 2. So therefore, we get that this is a strict inequality. All right. So we know that at least between every rational number, there is again another rational number. So between any two rational numbers, there's again another irrational number. That's kind of the idea we want to use for irrational, to put one in between. But we're going to have to do something a little bit trickier because, well, we have to use something that we know is irrational. So the average is going to be rational, so that's not going to help us. So let's think that I want to put this between something. Are there any numbers that we know are irrational? So can you guys tell me one number that we know is irrational? Pi. Pi is irrational. That is very good. However, I'm going to avoid pi because we didn't actually prove that pi is irrational in class. So have we actually proven that something's irrational in class? Showing that pi is irrational is actually a complicated proof, so that's why we were hesitant to do that in class. So the root 2, very good. So we're going to do something with square root of 2. So we're going to have to take the square root of 2. Now, the idea is I can multiply by square root of 2 or divide by the square root of 2 or things like that. But if I add the square root of 2, let's just try that, then what I'm going to get is a rational number plus an irrational number, which again will have to be irrational. So we know that irrational plus an irrational is irrational. So if I take P plus the square root of 2, I get an irrational number. All right. Now, square root the average. I love that example. However, it is possible that that would actually end up being rational. So if I want to think of an example, we could just take, if I do this correctly, I have to get 3 plus 5 over 2 is 4. And if I take the square root, I get 2. So actually, the square root of the average could technically be rational if we pick the appropriate things. So we want to show this is true for anything. So I'm going to stick with p plus the square root of 2. And somehow I want to compare this to p. I know that this is bigger than p. However, I don't know what q is, so I don't know how this compares to q. So now here's the thing is that I have to take this a step further and I have to think about, well, what is q minus p? Well, because q is bigger than p, I know this is greater than 0. So this is some number greater than 0. All right. So here's thought process. If I take 1 over q minus p, this is greater than 0. What is this going to be? This is going to be a real number, right? All right. With that in mind, this is a real number. Can I find something bigger than this? So if I take any real number, can I always find something bigger? That's my question. Just a yes or no. Yes. Thank you. Thank you, Penguin. So yes, I can always find a bigger number. And in fact, I can always find a bigger integer too, because I can always just keep going until I get to the next integer. So what I'm going to say here is that there exists an n such that n is greater than, for example, 1 over q minus p. So that's my first argument. Now, if I look at this, notice that 1 over, since n is greater than 1 over q minus p, this is a positive so I can multiply, this is a positive so I can divide. What I get is q minus p is greater than 1 over n. So if n is bigger than this, then 1 over n is smaller than this one. Now, what I want to say is, I'm going to take this a step further, and I'm going to say if I multiply this by the square root of 2, well, this is still a real number, so I can still find an n such that n is bigger than the square root of 2 over q minus p. Which means that n is smaller than the square root of 2 over n. Sorry, the square root of 2 over n is smaller than q minus p. Questions so far? Now I'm getting a little technical here. But the idea is that if I take this, square root of 2 over q minus p, then that's real numbers. So I can find an n that's bigger than it. So if I cross multiply here, I get q minus p is greater than the square root of 2 over n. So what I can do is, this n exists, so if I take p plus square root of 2 over n, notice that this is an integer, this is irrational, so irrational over an integer is irrational, plus irrational, so this whole thing is irrational. But this is less than p plus q minus p. So I'm going to cut that off there. But I know that this is p plus q minus p is greater than the square root of 2 over n. But p plus q minus p is just q. So what have I done? is, well, I've said p is less than p plus a positive number, root 2 over n. But because I picked this n so that this was smaller than q minus p, this thing has to be less than q. Therefore, we have found, or we've shown that there exists an irrational number between p and q. So between any two rational numbers, there is always a rational. All right, so let's think about what that means a little bit. What does that mean? Well, that means that for any two rational numbers, we can always find an irrational in between. So if we take all the rational numbers, for every rational, you can always find irrationals between them. So how many irrationals are there going to be? Well, a lot. So far, we've only proven that we have the square root of 2 or the cube root of 2, and so we have a few of them that we've mentioned in class. But now what we've proven without actually having to find them is that there are indeed infinitely many of these things. And in fact, there's a lot of them because between any two rationals, I can always find an irrational. And what it's going to turn out is actually that there are significantly more irrational numbers than rational numbers. What bit in the middle, Dylan? Go back to this part. Or this part. All right, so just to try to help here, what we did here was this is some real number, so I can always find a bigger integer. So we decided that was true together. So we introduced square root of 2 just because we know it's irrational. It's the only one that we've actually taken the time to prove explicitly that this is irrational. But now what I wanted was, I'm trying to put something between p and q. So instead of adding this is way too big. I want to find something that I know is irrational, but is still small enough to fit between p and q. So therefore, what I decided was I needed to pick an n so that when I divided the square root of 2 by n, I was smaller than q over p. So what this is all doing over here, and instead of going through all this again, I'm just going to point out the point is we found an n so that if I take the square root of 2 divided by n, this is going to become arbitrarily small, and therefore it's going to become smaller than q minus p. Therefore, if I take p plus this number, which is smaller than this, I'm going to get something which is strictly less than q. So I found something that is irrational between p and q. So now, as I was saying, what that means is that there are actually a lot of irrationals. In fact, there are going to be a lot more irrationals than rationals, which is fairly counterintuitive from what you may have seen in math classes before. Mainly, you focus so much on rational numbers that, yeah, there's a couple examples of irrationals, like square root of 2 or pi, but the point here is that I'm trying to say that there's not just a couple examples, there are in fact lots and lots and lots of examples, and there's so many examples that there are practically as many irrational numbers as there are real numbers. And we'll actually talk about that a little bit later in class if we happen to get there. But I wanted to point that out because until this point, you may not have noticed that there were so many irrationals. All right. Now, let's go ahead and look at our next theorem. I'm going to give you guys a couple minutes. Just sit at home and try to think about this. Is this true or false? I think you guys can do this one. So if you get the answer, type out true, and then we'll have to do a proof. Or type out false and give an example of x for where this is not true. Can can you hear me now? All right. Did you guys miss that entire explanation? All right, good. Sorry, not good, but I'll go back and try to do that again. All right. Sorry about that. Thanks for letting me know. All right. So what I was trying to point out is that we're trying to compare two functions. We have 2 to the x here, and we have 1 plus x here. And what I'm trying to do is just say, my theorem says that the 2 to the x is always bigger than the x plus 1. But we notice that just from the graph, that's not true in between 0 and 1. So if I pick anything in between here, I'm going to get a counterexample. So a nice one is 0.5. So 2 to the 0.5 to the square root of 2 is about 1.414, whereas 1 plus 0.5 is 1.5. So in this case, we have a counterexample for a theorem. What I was trying to say next, though, is that notice that at 0 they're equal, because 2 to the 0 is 1, and 1 plus 0 is 1. At 1 they're equal, because 2 to the 1 is equal to 1 plus 1 is 2. But for all integers, it is actually true that 2 to the x is bigger than or equal to x plus 1, because none of the integers would fall in this interval. Now, to prove that that's true is going to be a more complicated proof than just finding a counterexample, because you have to show it's always true. And it's an interesting proof that you may see if you take advanced calculus, because you really do need some calculus arguments here to talk about derivatives to show that that has to be true. So I'm just going to point out that extra foreshadowing for another class, that is something else that you could talk about, is not just is it true in general, but is it true for just the integers? And then showing that proof would be more involved than just finding one counterexample. Does that make sense? All right. We're running low on time. I'm just going to point out I have 2 more examples here. So if I want to say there exist integers a and b for which 25a plus 7b is equal to 1, what I'd have to do here is find an example, or I'd have to show it does not exist. And then if I wanted to do it for this one, I'd either have to find an example or show that it's not possible. It's actually easier to show that both of these are fairly easy, and so they make nice test questions. Notice for this second one, I have 25a plus 10b is equal to 1. Note, if I had an integer solution, then I should be able to divide both sides by 5. Then I get 5a plus 2b is an integer, but 1/5 is not, so we get a contradiction. So if I can find a common divisor, I can show that this is false. In this one, I can't find a common divisor of 25 and 7, so therefore this one is actually going to be true. So what you want to do is just check different multiples to see if you're ever off by 1. So I would try multiples of 7. You would get 7, 14, 21, 28, 35, 42, 49. Notice at 49, I'm off by 1 of a multiple of 25, which is 50. So if I take 50 minus 49, I do get 1. So A should be 2, and B should be negative 7. And so a lot of the homework problems look like this. I just wanted to go through them quickly so that you kind of know how to approach these. Is say, can I find a common divisor? If so, you can find a contradiction. If not, then find the multiples of those numbers until they differ by just 1. Thank you guys for joining me. Do you guys have any questions before I go? There is no homework tonight. I know there was one originally due, but that's because we weren't supposed to have a 2-week spring break. The next homework will be due next Monday, which I will assign for you Wednesday after class. I did delete that homework, but I did wait until today or yesterday. I forget which. Should have done it earlier, but I've been kind of busy trying to remodel my entire house. Any other questions? Hello, Magnus. All right. Well, thank you guys, and I will see you on Wednesday.